In most industrial facilities, process systems handle a lot of different types of fluids during the production of a product. These different fluids are moved from one location to another within the facility by piping systems. The flow of these fluids through the piping systems is controlled by valves. In order to keep fluids flowing smoothly through the piping systems to the various points where they're needed, the valves must work properly. And to keep valves working properly, operators have to know how valves operate. A diaphragm valve, like this one, is easy to recognize by its bell-shaped bonnet and a body that looks like this. A diaphragm valve uses a flexible diaphragm that's positioned on or near a weir or dam-shaped seat to control or stop fluid flow. A stud connects the diaphragm to a plunger. The plunger is moved by the valve stem. In this case, a hand wheel is used to raise and lower the stem. When the hand wheel is turned clockwise, the stem and the plunger lower the diaphragm, which presses against the seat to stop flow through the valve. When the hand wheel is turned counterclockwise, the diaphragm is moved upward and flow through the valve can begin. A diaphragm valve can be used for both on-off and throttling purposes. Also, the diaphragm in this type of valve serves as a seal that keeps fluid from coming in contact with the rest of the operating parts of the valve. This design makes diaphragm valves well suited for use in systems carrying corrosive materials, such as acids and caustics. Some diaphragm valves also contain a plastic liner to help protect the body of the valve from corrosive fluids. When you're operating a diaphragm valve, be careful not to use excessive force when you close it. Excessive force can cause the plunger to jam the diaphragm against the seating area, which could cut the diaphragm. If the diaphragm is cut, the valve may leak through from the valve inlet to the valve outlet, leak around the stem, or leak at the body-to-bonnet joint. Now that we've seen how diaphragm valves are constructed, let's take a look at the symbols that are used to represent them on piping diagrams. This is a symbol for a diaphragm valve. If the symbol on the piping diagram looks like this, it means that the valve is normally open during process operations. However, if the symbol for a diaphragm valve looks like this, the valve is normally closed during process operations. Other methods can also be used to show valve positions on piping diagrams. If a diaphragm valve symbol has the letters NO beside it, it means the valve is normally open during process operations. If the valve symbol has NC beside it, it means the valve is normally closed. Pinch valves are sometimes used to control the flow of heavy sludge and slurries, and they come in two basic types: enclosed body pinch valves and open frame pinch valves. Both of these valves are fairly easy to recognize. An enclosed body pinch valve has a pinched cylindrical body like this one. In an open frame pinch valve, all the valve parts are visible. This enclosed body pinch valve consists of a stem, a hand wheel, a bar or clamp, and a flexible tube through which fluid flows when the valve is open. As the hand wheel is turned to close the valve, the stem pushes the bar against the tube. This squeezes or pinches the tube between the bar and the valve body, stopping the flow of fluid through the tube. In some pinch valves, the bar may be connected to the top of the tube, here. This connection helps the tube return to its original shape as the valve is opened. Since most of the valve's components are outside of the flexible tube, there are no components within the flow path of the fluid through the valve. Since there are no components in the flow path for materials to collect on, pinch valves are ideally suited for the handling of fibrous slurries and sludge. On a piping diagram, pinch valves may be represented by this symbol. If the valve symbol looks like this, or if it has the letters NO beside it, it's normally open during process operations. However, if the symbol looks like this, or if it has the letters NC beside it, then the valve is normally closed during process operations. Check valves are usually used in piping systems where the reversal or backflow of fluid could upset the operation of a process or damage equipment, such as a pump. Now, even though there are many different designs of check valves, most operate in the same manner. As long as fluid flows through a check valve, the valve stays open, but when fluid flow stops or reverses, the valve closes. In this part of the program, we're going to take a look at three different types of check valves: a swing check, a lift check, and a ball check. A swing check valve looks like this. It consists of a valve body, a seat, a disc, an arm, and a pivot pin. The disc is hinged at the top of the valve body by means of the arm. The pivot pin goes through the valve body and the arm to allow the disc to hang in place. The disc closes against the seat to block fluid flow. When pressure is under the seat and disc, the disc pivots or swings away from the seat, opening the check valve and allowing flow through it. When flow through the valve stops, the force of gravity pulls the disc onto the seat. As fluid flow through the valve starts to reverse, backflow pressure pushes the disc against the seat to fully close the valve. In some cases, the arm that holds the disc is weighted to assist in closing the valve. In other cases, a spring may be used to help close the valve. It's also common to find the direction of flow indicated on the outside of a check valve's body. Usually, an arrow is cast into the valve body to help ensure that the valve is installed with flow in the proper direction. As long as flow is constant, the disc will remain raised. If flow is intermittent, the disc may repeatedly rise and fall, slamming against the seat. This action can damage the disc and the seat and result in leakage through the valve. This condition can often be detected because as the disc slams against the seat, noise and vibration are produced in the piping. When you detect this kind of problem, report it to your supervisor. In addition to problems that may result from operating with intermittent flow, swing check valves also aren't very effective for controlling the flow of fluids containing solid particles. That's because the solids can accumulate between the disc and seat and prevent the valve from closing. Since swing check valves may not close because of the buildup of solids on their disc and seat, you should never rely on check valves to isolate a component or system from fluid pressure in another part of a process system. This could prove to be extremely dangerous in situations where a process system is about to be opened up for maintenance. In cases like these, always take measures such as shutting the appropriate isolation valves to ensure that a system is properly isolated. The next type of check valve we're going to look at is a lift check valve. A lift check valve consists of a valve body, a disc, a seat, and a guide. The guide keeps the disc lined up with the seat as the valve operates. This ensures that the disc will align with the seat as the valve closes. When fluid flows through a lift check valve, the disc lifts. And when flow stops, gravity pulls the disc back onto the seat. Fluid backflow will push the disc tight against the seat. Lift check valves can be used in either horizontal or vertical piping runs. This type of lift check valve would be used in a horizontal piping run, and this type would be used in a vertical piping run. Now, the last check valve we'll discuss is a ball check valve. This valve consists of a valve body, a seat, and a ball. When fluid flows through the valve, the ball is pushed out of the seat. As the ball is lifted, it rotates in the fluid flow. Since it's difficult for solid materials in a fluid to stick to the spinning ball, these valves are useful for handling liquids containing scale and sediment. This self-cleaning effect helps ensure that the valve will close properly. When flow stops, gravity pulls the ball onto the seat. Backflow will then hold the ball firmly on the seat. Like the lift check valve, the ball check valve can be used in either the horizontal or vertical position. Check valves may be represented by many different symbols on piping system diagrams. A few are shown here. However, most of the symbols have one thing in common. There is usually some type of notation on the symbol that indicates the direction of flow through the check valve. For example, this symbol uses an arrow to show the direction of flow, while this symbol uses a dot on one end of the diagonal line across the center of the symbol. This dot represents the point where fluid enters the valve. So on this symbol, flow would go through the valve in this direction. Liquids and gases in industrial facilities are often contained under pressure in closed systems. These types of systems can remain pressurized only as long as the system is closed. And because the systems are closed, if the pressure increases excessively to a point greater than the system can stand, the equipment or piping will rupture. Excessive pressure can occur for a variety of reasons. For instance, starting or stopping equipment without proper valve positioning can result in excessive system pressure. Excessive system pressure can also occur when equipment malfunctions. For example, if a line from this pump is blocked when it should be open, an increase in pressure can occur. Excessive pressure in systems can be relieved by relief valves, like the ones on this liquefied gas tank. A relief valve consists of a valve body, a disc, a seat, a spring, a valve stem, an adjusting screw, and a lock nut. The valve body or casing provides a path for the liquid to flow and holds the other valve parts in their proper positions. This is the valve's inlet, and this is the outlet. The disc rests on the seat and is held in place by the spring when the system is at normal pressure. The valve stem guides the disc up and down, just like in other valves. A relief valve is set to open when the pressure in a system reaches a predetermined value, say 200 psi. If pressure in this system reaches 200 psi, the pressure on the disc begins to overcome the force of the spring, and the disc begins to lift off of the seat. As this happens, the pressurized fluid is released through the valve's outlet. If the pressure in the system continues to rise, the disc will continue to lift until it has risen as far as it can go. As soon as system pressure begins to decrease, the valve begins to close. And as the system pressure decreases to just slightly below 200 psi, the force exerted by the spring will push the disc back onto the seat. The adjusting screw is used to change the force exerted by the spring. Tightening the adjusting screw increases the force exerted on the disc, thereby raising the pressure setting at which the valve opens or lifts. Loosening the adjusting screw reduces the amount of force on the disc and allows the valve to open at a lower pressure. The lock nut holds the adjusting screw in position after the force exerted by the spring has been set. The top of the assembly is usually covered by a cap that protects the adjusting screw. On a piping system diagram, a relief valve could be represented by any of these symbols. The relief valve setting is often included beside the symbol for the valve. Because of the way it operates, a safety valve, like the one on this steam line, is well suited for use on steam or other gas systems. A safety valve is designed to open wide very quickly and to stay open until the pressure in the process system has been reduced to a pressure that is less than the opening pressure of the valve. Since the valve opens wide quickly, a large volume of gas can be rapidly vented from the process system to reduce pressure. Getting a safety valve to open wide quickly can be done in a couple of different ways by valves with different designs. Let's look at a typical example of a safety valve to see one way it's done. This safety valve consists of a valve body, a disc, a seat, a spring, a valve stem, an adjusting screw, a lock nut, and a manual release lever. The manual release lever is used to test the operation of the safety valve. The disc of a safety valve has a lip that isn't exposed to system pressure when the valve is closed. The center portion of the disc is always exposed to system pressure. If the valve is set to open or lift when the system pressure reaches a preset limit, say 200 psi, the disc will start to lift when that pressure is reached. When this happens, the lip of the disc is suddenly exposed to system pressure as well. And since a larger area of the disc is now exposed to system pressure, there's more force exerted on the bottom of the disc. This increased force overcomes the force exerted by the spring and causes the disc to pop open to about a 60% open position. This allows a large volume of liquid or gas to escape rapidly. If pressure in the system keeps getting higher, the pressure acting on the bottom of the disc will also increase and cause the disc to lift even higher. Once the excess pressure in the system has been relieved, the system pressure will begin to drop. As pressure goes down, the force acting on the bottom of the disc also decreases. Eventually, the force exerted by the spring takes over and pushes the disc down. However, when the system pressure gets down to the point where the valve popped open, 200 psi, the valve still doesn't close because the lip of the disc is still exposed to the pressure of the escaping liquid or gas. The valve won't close until system pressure drops below the pressure needed to pop the safety valve open. The opening pressure setting can be changed using the adjusting screw. Tightening the adjusting screw increases the force exerted on the disc, thereby raising the pressure setting at which the valve opens. Loosening the adjusting screw reduces the amount of force on the disc and allows the valve to open at a lower pressure. The lock nut holds the adjusting screw in position after the force exerted by the spring has been set. On a piping system diagram, a safety valve could be represented by any of these symbols. These symbols are similar to the ones used to represent relief valves. Often the valve's operating set point is also included beside the symbol. In this topic, we've seen how relief valves and safety valves are constructed and how each of these valves operates as system pressure changes. We also saw how you could identify these valves on piping system diagrams. Now let's try some practice questions.